Let me introduce the so-called unit impulse function. The other name for the unit impulse function is the Dirac delta function, after the great scientist Paul Dirac. So for the definition of the unit impulse function, we are going to use a very simple way, and we are not going to the deep of the Dirac delta function. So let us start with the window function, which window function is 0 everywhere except the time interval 0 to capital T. The value of the function is not 1, but 1 over capital T, and this is why the area of this function is usually equal to 1. It is capital T wide and 1 over capital T high function. So the area of this function is usually 1. This is why we are going to call it unit impulse function. So the representation of the function is 1 over t multiplied by the window 1 of t minus 1 of t minus capital T. But now we are going to decrease the value of capital T. So if we decrease the value of capital T, the height of the function is going to increase, because the area of this function is usually equal to 1. But there is the limit when the capital T goes to 0 closer and closer, and this is why 1 over capital T is increasing and increasing to infinity, and this is the limit that we are going to denote by this arrow, and this is the so-called Dirac delta function. So on the left we have got a unit impulse function, on the right we have got the special unit impulse function, which name is Dirac delta function. So this is the Dirac delta function, which is a function with 0 everywhere except the time 0, and here the area is equal to 1. This is the definition of the Dirac delta function. So we can write the following. The delta t, the Greek letter delta is used for the Dirac delta function. So the delta t is equal to the limes of the window function, 1 of t minus 1 of t minus capital T over capital T, and t goes to 0. And this is the Dirac delta function by definition. And as we can see, this is from the definition of the derivative, it is equal to the time derivative of the 1 of t function. So if we have got a step function and we have to take the derivative of this function, I mean the step function, we are going to get a Dirac delta function at the jump of the step function. So delta t is equal to the time derivative of 1 of t by definition. By definition, the integral from minus infinity to plus infinity of the Dirac delta function is equal to 1, and the integration limits from minus infinity to plus infinity can be rewritten as minus 0 to plus 0, because the Dirac delta function is at the time t equal to 0, and it can be written as from minus 0 to plus 0. So this is the time interval where the Dirac delta function is appearing. So once again, the Dirac delta function is a special unit impulse function. Special because the width of the function is equal to 0 and the height of the function is equal to 1 over capital T, and this capital T goes to 0. The other thing is that the area of the unit impulse function and the area of the Dirac delta function r equal to 1 by definition. Later, it will be very important thing. And the last, the Dirac delta there is a correspondence between the Dirac delta function and the step function. That is, the time derivative of the step function is the Dirac delta function. And last important thing which we are going to use later, if we have got a function, any function f of t, and there is a translated Dirac delta function translated to capital T, that is delta t minus capital T, and we multiply these two functions, it's very easy to see that the multiplied function will be 0 everywhere except the value of capital T. So ft multiplied by delta t minus capital T will be equal to f capital T. So here we have to put this value multiplied by delta t minus capital T, because the result is 0 everywhere except this value.